Hey, welcome to a quick video looking at vector components. I just wanted to talk really quickly about what they are and offer a little help in finding how to calculate them if you're having any trouble with that. Just a quick review from our notes. Vector components, they're perpendicular vectors that we can get rid of some diagonal vector and replace with these, because adding up diagonal vectors is a pain in the butt, but we can replace some diagonal vectors with x or y components. Just as on this plotting this helicopter's path, it was much easier to work out how far east and how far north it went. Okay, so we're going to be using trig identities for that. Now these trig identities, you're used to SOHCAHTOA, where sine of theta equals opposite over hypotenuse or something like that, but we are going to rearrange these in ways that are useful for what we need. So for example, our sine equals opposite over hypotenuse, we're rearranging that because opposite, one of the legs of the triangle, well, to find our components, we need to find the legs. So opposite is one of those, and we can find the opposite by calculating hypotenuse times sine of theta. Similarly, we can find the adjacent side by calculating hypotenuse times cosine of theta. So there's nothing wrong if you want to set up your triangles and solve from the original SOHCAHTOA equations, but we use these so very often to find our components that it's worth just kind of memorizing these guys to work with. Now, to go in reverse, sometimes we need to find the hypotenuse and the angle. In other words, this is getting back to a diagonal vector. So to find the diagonal vector, the hypotenuse, we're going to use Pythagorean theorem. We're going to use our one leg squared plus the other leg squared and square root it. A squared plus b squared equals c squared. And to determine an unknown angle, we're going to use our inverse trig function. So the easiest thing to do, our assumption is that you know opposite and adjacent, and what you need is to find the hypotenuse. So if I take the inverse tangent of opposite over adjacent, that will get me my angle. And quick note here, the theta that was supposed to come through in the typography didn't, so do me a favor and please correct that in your workbook. Okay, but let's look at actually doing that with a couple diagonal vectors. And this is the main point of the video, is getting to, okay, you're telling me this, but how do I do it? So we draw a triangle. I have a diagonal vector here. I make a triangle, right triangle, that includes the diagonal vector as the hypotenuse, and we want it to include the angle that we have. So if this is vector A, let's say, then this component here would be AX, and this component here would be AY, our horizontal component and our vertical component. Now, we need to determine how to find these, and a lot of you guys will habitually go to sine or cosine for y or x because that's the way it always is in math class. But that's assuming you've set it up a certain way. That isn't always the case. Here's what's always true. The opposite is always linked to sine. The adjacent is always linked to cosine. And what we have here when we know the diagonal is our hypotenuse. So if I want to find my opposite, AY is opposite. The opposite is the hypotenuse times the sine of our angle. So 15 meters per second times our sine of 35 degrees. Now when I calculate this, I want to make sure that my calculator is in degrees, and when I put that in, I find that I get 8.6 meters per second. And the amount and the units, they're going to match up with the original vector. So that's my AY. What about my AX? So my x component was the adjacent. The adjacent is hypotenuse times cosine of theta. So 15 meters per second times cosine of 35 degrees. And when I put that one in, I get about 12.3 meters per second. So that means that saying 15 meters per second at an angle of 35 degrees is a little hard to visualize. But what we can say is that this object is moving 8.6 meters per second upwards and 12.3 meters per second to the side. The main things that we need to do is make sure we draw the triangle correctly with the original vector as the hypotenuse, and that we correctly identify the opposite and adjacent on our triangle. So, if you haven't already, pause the video, take a look at our second vector over here, vector B, and see if you can determine the x component and the y component for vector B. Okay, you've done some setup. Let's talk our way through it. I need to draw a triangle here. BY, BX. And please note, my BX is opposite from the angle. My BY is adjacent to the angle. And my diagonal vector, of course, is our hypotenuse. So, determining BX here. If BX is the opposite, then that means it's going to be the hypotenuse times the sine of theta. So I'm going to show that work down here a little more clearly. Hypotenuse times the sine of theta. So 32 meters times the sine of 25 degrees. And that's going to get me a component of 13.5 meters. And my BY, well, my BY is adjacent, and my adjacent is hypotenuse times the cosine of theta. So 32 times cosine of 25, and I get about 29. So x component, y component. Now, please note that this calculation method does not give us direction at all. So we had to look at this and say, oh, this 13.5, that's to the left. And if I'm calling left negative, then it's on me to assign the negative. If I have a component that is up or down, I have to determine whether I should call that positive or negative. It is up to us to assign positives and negatives. Okay, one other thing we're thinking about for components down here. Not all components need us to do trig. And by the way, you don't have to show this whole trig setup every time. Even in this class where we expect you to show so much work, it's fine if you just skip straight to showing the calculation of 32 cosine 25 to find the components, but it is up to you to make sure that you are doing it correctly. Okay, so these guys though, we don't always have to do trig, and why not? Because if there's no diagonal, there's no trig necessary. So for example, our gravitational acceleration. Our acceleration due to free fall gravity, about 10 meters per second squared, just down. So if I'm drawing that as a vector, it might look like that. And in fact, I just went ahead and labeled this out of habit. Acceleration in the y direction, 10 meters per second squared down. That is the component. That is our y component. Well, what is the x component for this? Well, let me ask you, how much does gravity pull sideways? None. And this vector is straight up and down. It has zero component in the x direction. So, not only do we need to be able to do trig, I have to recognize when there is a quantity that is purely horizontal or purely vertical, and know that the other component then for that would be zero, just like our acceleration here. Vice versa, if you have a car that's traveling along, don't make fun of my art, and it has a velocity of 20 meters per second. Well, if it's on a flat surface, the Vx for that is 20. And the Vy, if it's not moving up or down, the Vy component is 0. All right. Have fun with components. Look around you. You'll see them all over the place. We use them all over the place. Happy physicsing.